Welcome back everyone. In this lecture we will talk about cosets, the notion of cosets. So, I will first begin with many examples and then we will later see the definition of cosets and basic properties of cosets. Okay, so let us actually start with some familiar examples. So, let us take the group of integers z. So, this is the group of integers with respect to addition. Okay. So, then one can actually take for example, a subgroup. Okay. So, let us consider this 2z. So, let us denote it by h. So, g is our z and h is our 2z. So, this is actually a subgroup of g that we have already seen. So, now we have these following sets that are actually related to this subgroup. Okay. So, what are they? So, this is something already appeared in our previous discussions. For example, I can take any integer, let us say a in z. Okay. So, for any a in z, so consider this a plus 2z. So, what is this? So, this is a plus 2n where n comes from z. So, as a set it is just a translation of this subgroup 2z by this element a. So, what is important about this subset? Okay. So, these subsets more or less look like the group that we started with, that is H. Okay. For example, it is not that hard to see. Okay. This I will leave it as exercise. So, you can verify because this is about integers. So, if we take these sets, okay, which are subsets of z, a plus 2z, and then let us consider another subset b plus 2z. So, we can ask this question when they are equal. Okay. For example, if I consider 2 plus 2z, so that will be same as z plus 2z. So, this is not very hard to see. So, there are integers for which these sets actually become equal, a plus 2z becomes equal to b plus 2z, and it is not hard to determine when it will happen. So, this will happen if and only if this a minus b, it is an even integer. Okay. So, this belongs to 2z. So, in some sense we are actually looking at all possible translations of this subgroup 2z, and then we see that if we consider them, then they are actually equal if and only if this a minus b is actually even integer. And there is another important property. Okay. So, either they will be equal, okay, for any a comma b integers. If you consider a plus 2z, either it is equal to b plus 2z, or if we take the intersection a plus 2z intersection with b plus 2z, so that will be empty. Okay. Again, this is not that hard to actually see. So, what one needs to prove, okay, let us verify this fact. If they are equal, then there is nothing to prove. Okay. Then assume that they are not equal. Okay. Then we want to prove that the intersection must be empty. So, we can actually work like this also. For example, we can start with assuming the intersection is being non-empty, because if it is empty then there is nothing to prove. Okay. So, assume, okay, a plus 2z intersection with b plus 2z. So, this is actually non-empty. So, that means there exists x such that x can be written as some a plus 2n and b plus 2n. So, then it is clear that this implies a minus b, this is in 2z. Okay. So, then from the previous exercise you can see that, so this a minus b, if it is even, then the corresponding sets. Okay. So, these will be called cosets in this case. So, they are actually equal. Okay. So, then this implies a plus 2z is same as b plus 2z. So, this is something I will leave it to verify. Okay. This is not hard to verify. So, that means these sets they are somewhat very special kind of sets defined using this subgroup 2z. Okay. So, in particularly using this property you can see that they form, okay, if you collect them together as subsets of z, they form a partition of z. Okay. And it is not hard to see. So, there are only 2 of them. Okay. So, for example, one corresponds to 0 and another corresponds to 1. So, this is something we have already seen. These are all the total number of a plus 2z cosets corresponding to the subgroup 2z. Okay. So, then it is not hard to see z is written as 0 plus 2z union disjoint union 1 plus 2z. So, this is something we have seen already. I am just recalling in this setting. Okay. So, similar thing happens for any subgroup of z. Okay. So, let us consider now general subgroup. Okay. Let us take for example n z. Okay. Again we can define the cosets corresponding to this n z. So, what it will be? It will be some x plus n z, which is by definition x plus some k times n, where k is running over z. Okay. So, this is the coset corresponding to x and the subgroup n z. Okay. So, now again I will leave it to you to verify. Okay, this is something we already verified, that is why I do not want to do it again. So, this is not that hard. You can prove that x plus n z is same as y plus n z if and only if this n divides x minus y, or x minus y is multiple of n. Okay. And if you take 2 of them, x plus n z intersection y plus n z, if this is non-empty, then that would imply that x plus n z is same as y plus n z. So, in particularly this collection x plus n z, when x runs over all integer, that will form actually the distinct sets that will form a partition of z. Okay. And it is not hard to see, there are exactly n number of such cosets, for example, corresponding to 0, corresponding to 1 and corresponding to n minus 1, etc. So, these are all the set of all cosets. Okay. So, these are all something that we have already verified, that I will leave it to actually check again. So, this is some example that we have seen already. So, that comes from the group of integers. So, now let us move on to geometry, okay, and then consider for example vector spaces and then their subspaces. So, let us take something very simple. For example, let us consider R2. So, this is the 2-dimensional real space. So, then it is not hard to actually see that any 1-dimensional subspace of this will be a subgroup. Okay. So, R2 can be considered as actually group with respect to the addition, that is the coordinate wise addition. Okay. If I take 2 elements x bar y bar in R2 plus, where x bar is written as let us say x1 x2 and then y bar is written as y1 y2. So, then x bar plus y bar defined to be x1 plus x2 y1 plus y2. So, with respect to this actually form a abelian group. Okay. This is something part of the definition of vector space, and it can be verified for this particular addition. Okay. Now, one can take any 1-dimensional subspace of R2, let us call it V. So, this is let us say 1-dimensional subspace of R2. Okay. For example, one can take only V to be x axis. Okay. Here the examples, and then one can take V to be y axis, both of them are actually one dimensional subspace. And it is not hard to see actually any one dimensional subspace of R 2 that will actually pass through the origin. Okay. So, basically any one dimensional space, so it will look something like this. So, this is what your V. Okay. So, this V will be just some lambda times some x naught, where lambda will be in R, where x naught is actually some unique vector that is determined by this V. So, any subspace, okay. So, let us say V x here, this is a subspace, V y, this is also a subspace. In particularly for any x naught, so V x naught will be just lambda x naught, where lambda coming from R for x naught in R 2. So, this is again a subspace of R 2. Okay. In particularly it is a subgroup of R 2. So, this is what the V looks like. So, let me draw it again. Okay. So, this is your R 2. Okay. So, let us take first of all x axis itself. Let us consider this V 1 comma 0. Okay. So, let us rewrite this notation using the thing that we have already introduced. So, this is V 1 comma 0 and this is 0 comma 1. So, what is this? This by definition, this is those lambda comma 0, where lambda coming from R, and this is 0 comma lambda, lambda coming from R. Okay. So, now if we take this V 1 0, so which is actually x axis, V 1 0, this is x axis. So, now what we can do, we can actually translate this x axis by any element of R 2. Okay. Let us take some element x, call it x 1 comma x 2 from R 2, and then as before that we did it in the case Z. So, in Z what we did, so we took this subgroup n Z and then we looked at possible translation of this n Z by elements of Z. Okay. That is what we called it coset. Okay. So, geometrically speaking, this has very nice interpretation. Okay. So, basically coset, that is something looks like that subgroup, but it is not a subgroup, it is some kind of translation. Okay. So, that is something we have to make sense of for the general group. For that purpose, let us see these practical example, then we will generalize. So, now as before, given this element x bar inside R 2, we can consider the translation x bar V 1 comma 0. Okay. So, note that this x bar plus V 1 comma 0, it is a translation of x axis. So, translation of x axis will be again look like x axis only, okay, but it is just translated a bit. So, let us algebraically write down what it is. So, if you just work this out, you can see that you will be adding x 1 comma x 2 plus lambda comma 0, where lambda is just running over R. So, that means, so this is going to be exactly equal to x 1 plus lambda comma x 2, where lambda is running over R. So, what is this? So, if you write it, you can see that, so this x bar plus V 1 comma 0 is exactly equal to, so because this x 1 is fixed, lambda varying over R. So, this is going to give you some x dash or lambda dash, okay, let me call it lambda dash, and then comma x 2, where lambda dash also again varying over from R. Okay. So, but what it is? It is a line. For example, if you take x 2 to be 1, okay, if you take x 2 to be 1, then this is line that is parallel to x axis passing through 0 comma 1. Okay. So, depending upon x2 positive, let us say x2 positive, then x2 will be somewhere here. Okay. This is the 0 comma x2. So, this is exactly this x bar plus v1 comma 0 is just a line that is parallel to x axis, but it passes through that 0 comma x2. So, this is your x bar plus v1 comma 0. Similarly, when x2 is less than 0, then this x2 will be plotted here. Okay. So, 0 comma x2 will be plotted here, again it will be a line passing through that. So, this will be x bar plus your v1 comma 0, and this will be just a parallel line, okay, that passes through 0 comma x2 parallel to this x axis. So, this is your x axis. Okay. So, this means what? This means this x bar plus v1 comma 0, even geometrically speaking, it looks exactly like x axis, it is just a translation of x axis. Okay. So, when you do this for vector spaces, it becomes actually very clear what we are really doing, but this is something we want to do it for actually any group. Okay. So, now let us consider a line that actually passes through just origin. Okay. Let us take again R2 and then consider this line that passes through just origin, okay, any line. So, that is your let us say Vx naught. So, then I will leave it to you to check if you translate this line with respect to some x bar, okay, if it is x bar plus Vx naught if you take, then that will be just a line that is parallel to this Vx naught. So, this will be your x bar plus Vx naught. So, this is something I will leave it to verify. Okay. So, here are some more again geometric examples. Okay. For example, let us consider now R3. Okay. So, for example, you can take just V to be xy plane. The axis that I am actually denoting it by xy z axis. Okay. So, this V I am taking it to be xy plane. So, let us draw this picture. So, this is going to be our 3D space. Okay. Let us call this is x, this is y. So, this is the plane that we are talking about. Okay. So, now for example, if you take some x bar inside R3, okay, where x bar is given by x1, x2, x3. So, then if you consider x bar plus v, so then it is not hard to work it out what it will be. So, in xy plane the z coordinate will be 0. So, this is x comma y comma 0 where xy comes from R. So, in particularly, so this x bar plus v will be some x comma y comma x3 where again xy will come from R. Okay. So, depending upon let us say x3 positive, then it will be a plane that is actually parallel to x axis. Okay. So, this is the plane that we are going to get x bar plus capital V if x3 is positive, and otherwise it will actually go down to the below. Okay. So, geometrically it is clear that if you just translate the plane, you will again get the plane. But so, you can see that there is a natural bijective correspondence between the xy plane and its translation. Okay. That is also clear. The same thing is clear even in the R2 case. Okay. So, now let us have some example which is not linear. Okay. So, for that purpose let us consider the complex plane, okay, that is your C. So, this is a group with respect to addition. The one that I wanted actually the non-zero complex numbers with respect to multiplication. Okay. So, this is a multiplicative group. Okay. So, this is yeah not linear. Okay. So, then what it will be, it is just the punctured plane. So, you have removed this complex number and then you have the punctured plane, and then what we can use this polar coordinates to denote elements of C star. For example, given z in C star, one can write z as some r times e power I theta, where r is coming from, actually r cannot be 0. So, it has to be come from the positive real line, and then theta can come from 0 to 2 pi. Okay. So, now we can take H to be your subgroup, that I can take it to be S1. Okay. So, what is S1? S1 by definition it is a unit circle inside C cross. This is those z in C cross such that mod z is 1, and it is clearly a subgroup because the product of two unit vectors will be unit, inverse of unit vector is again unit. So, then it is easy to see that this unit circle, okay, this is the unit circle, it is a subgroup of, okay, subgroup of C cross. So, now where it is, actually it is, you can draw it like this. So, this is our S1. Okay. So, now what we can do, we can take some z which is some r times let us say e power I theta. So, which is an element of C cross, and then as before. So, in the previous cases what we did translation of the subgroup, okay, because the binary operation there is actually addition, but here the binary operation is multiplication, the translation amounts to multiplying this z by the subgroup S1. Okay. So, one can naturally consider this z times S1. So, what it is, this is just a notation, okay. This is something that we need to understand, we have not defined what it is. So, this is something I am defining it to be. So, this is just a notation. I am writing this z times S1 as what it is z times z dash, where z dash comes from S1. So, this is the natural definition of this set z times S1, which is a subset of this C cross. Okay. So, now if we do some algebraic calculation, we can see that what is this z times S1. So, this z times S1, because z is nothing but r times e power I theta, z dash is given by e power some I some xi. Okay. So, then z s dash will be set of all r times e power I theta plus xi. Okay. Now, this theta is fixed. Okay. So, then you are actually going to run over this xi from 0 to 2 pi, but because of the winding you can see that. So, you can actually, oh sorry, this is something we should write it as 2 pi xi. Okay, let's change the indexing set a bit, so that we do not need to worry about this winding. Okay. So, let us take this theta comes from r. Anyway, this does not change anything. Okay. So, then it is clear this indexing set will be changing a bit. E power I xi. So, then this theta plus xi will run over r. So, that so this xi is running over r, which is same as r times e power some I theta dash, where theta dash will run over r. Okay. So, but what it is? So, as a set you can see these are all elements that has exactly the length is r. Okay. The modulus of r e power I theta dash is nothing but r, since r is positive number. So, geometrically speaking, this z times S1 is nothing but another circle which has radius r and center 0. Okay. So, this is going to be your new element. Okay. So, exactly this is our EZ S1, and of course, depending upon the value of mod Z, the mod Z equal to R, if it is greater than 1, then this is what we get. If it is for example less than 1, okay, then we will get the inner circle. So, this is going to be inside if this is going to be our Z S1 if mod Z is less than 1, and of course, mod Z equal to 1, you will get this S1. But what is important here, okay, because we have the binary operation which is multiplication, and by multiplying this group S1 by this fixed Z, we get some new object which exactly looks like S1, okay, that is what important, okay, and there is a natural bijective correspondence between this S1 and Z S1, and you can see that. So, the geometrically also the shape of this is actually not changing, okay. So, most of the time the binary operation that you actually consider, depending upon the space that you are working with, it will be very nice map, okay. So, that nice map is actually going to preserve most of the things, and of course, depending upon the modulus either being greater than 1 or less than 1, it actually either squeezes the circle or expands the circle, okay. But the shape of the circle, I would say it does not change. Okay, this is some one good example of multiplicative side. So, we can also create, we can also actually do more example like this. So, for example, one can take this again the multiplicative group C cross, okay, and then I can look at this R plus. So, which is the positive real line. So, this is those R such that R is positive. So, geometrically speaking, so you have this punctured plane, okay. So, let us draw it properly. So, you have the punctured plane, and then what is my R plus? R plus is this, okay. So, now again we can use the polar coordinates and then try to determine, so what will be the coset corresponding to this subgroup, okay. So, as before, what will be the coset? For example, I can pick some Z which I can denote it by R times e power I theta. So, this is something you can fix, and then look at this Z R plus. So, you can easily see that the modulus value is actually not going to change, do anything. So, this is going to be exactly equal to R times e power I theta times some R dash, where R dash comes from open 0 comma infinity. So, then this is going to be e power I theta and then R plus, okay. So, then geometrically it is clear that, so this is going to be this new ray, okay. This is the ray is R plus, and this is the ray e power I theta R plus. So, where this is the angle theta that it makes with the x axis. Of course, theta, if it is depending upon theta, the ray actually changes. So, from these examples, so what are all the important things that we have actually seen? Okay, first of all, we have a natural bijection from the coset and the group and the subgroup that we have actually started with. So, that is one thing, and you can see that these cosets, okay, so that is actually going from, so they are changing and they are all disjoint, that is what important, okay, and they cover entire. So, if you take all the rays, okay, where the theta actually varying, then it is easy to see. So, they all cover actually our group C cross. So, in particularly they form a partition of our group, okay. So, these are all the properties of cosets. So, that we will actually formally define and then prove it later. But anyway, before that I also want to actually give you somewhat more sophisticated examples, okay. Again I will leave it to actually work with them. Okay. So, it will be very fun. So, for example, what one can do, one can take roots of unity. Okay, let us call it un. So, this is those z in the multiplicative group C cross such that z power n is 1, and one knows that this is a finite group and this is generated by the primitive nth roots of unity. So, the primitive nth roots of unity you can denote it by this e power I 2 pi by n. Okay. So, then it is clear that the group is actually generated by this. This is a cyclic group, and this is being a subgroup of C cross. Okay, one can ask what will be Z un, okay, for any Z in C cross. Okay. So, just try to actually identify so what these Z un are. Okay, and then try to parameterize them. Okay, and then see what you are getting. So, I will leave this as exercise. And similarly, one can also work with this rational group, okay, with respect to addition. So, this is my first exercise and this is the second exercise. So, you can work with this rational numbers q plus. Okay. So, now what one can do, so naturally this z is sitting inside q. Okay. Similarly, for any n, n z also sitting inside q. So, I want you to actually look at all the translation of first of all with respect to z. So, what will be, what are all this x plus z, find out some parameterizing set for all of them, and then what is about x plus n z, okay, for some fixed n. So, with respect to these two subgroups, so determine all possible translations or the cosets. So, these are all the cosets. Okay. So, as an exercise you should try to determine them, and then that is what gives you better understanding of cosets. Okay. So, I will stop here. Actually, we have seen many examples that are more practical and geometrical. Okay. So, these examples we want to actually generalize and abstract them and then define cosets in any given group and subgroups. Okay. And then we will define them and then we will see some properties of these cosets as noticed in these examples, and then we will use them and then try to understand the group property and then subgroup properties. Okay, I will stop here. Thank you.